All right, good evening, stargazers, and welcome to Starry Nights with us here at the SFU Trottier Observatory. Thank you for joining me tonight, and hopefully all the audio's coming in and everything sounds fine. If not, please let me know in the stream, but I think we've gotten pretty good at this now, so I think we're doing okay. My name's Matthew. I'm going to introduce everyone else who's helping me. I got three moderators in the chat who are helping us tonight. There's Sarah, Zena, who are both observatory staff members, and of course we also have Ken joining us today from the Royal Astronomical Society, which is awesome because we used to tag team with Rask for Starry Nights when we were there in person, but we are not there in person anymore these days. So we're glad to have Rask joining us. So Ken, thanks for coming on and helping us. All three of them, Sarah, Zena, and Ken, will be helping to answer some of your questions in the chat when I can't get to them. Just to kind of give you an idea of what this all sort of looks like. It's a lot more complicated than just sitting at the normal observatory because we have like the actual observatory software, but then we've got like the streaming software, and then of course we're doing like Vocal Live, and then I've got a list of stuff that we're doing. So we're always kind of like juggling a bunch of things when we're doing the live stream, which is why we have people helping out and moderating the chat. So thank you to Sarah, Zena, and Ken for helping out today. Okay, so the sky conditions look pretty good this time around. Last week, if you were joining us, we had about half of the targets got clouded out, unfortunately. So right now, things look pretty good from here, where I am, which is actually sort of like near Boundary Road, right between Vancouver and Burnaby. But where the telescope is, it's sometimes different. Burnaby Mountain tends to have its own sort of microclimate and have its own clouds that sometimes pile on top of the mountain, even where it's clear everywhere else. So hopefully it is clear. And right now, to get an idea, I've been looking at Jupiter, and that's going to actually be our first target. I find when Jupiter is out, I can't really deny looking at it. And so here we go. Planet Jupiter, 660 million kilometers out into space, 1,321 times Earth's volume. And there it is. Jupiter right now is the brightest object in the night sky. So if you get outside and take a look, that bright point kind of looking southeast in the sky is in fact Jupiter, the largest planet in our solar system. And now that we know, kind of have an idea of how solar systems form, this is one of the amazing things that we learned about astronomy. Astronomy, we're kind of talking about this last week, but astronomy is literally digging into the memory of the universe. And so, you know, in the past, we thought the Earth was flat and maybe it was the entire universe. But now we know, kind of looking out into space, we started through astronomy really unlocking the rest of the universe, coming to understand how many planets were in our own solar system, but also understanding and beginning to understand how planets form. And we've been able to take images of forming solar systems, but we're not always entirely sure how gas giants like Jupiter form. We don't know if they formed directly from gas, so is Jupiter gas all the way through, or was it started off as a protoplanet that would have been made of rock or planetesimal? It could have been actually a core as large as our own planet, Earth, and then the atmosphere accreted around that world, and we're not entirely sure. And in fact, the Juno probe, which is orbiting Jupiter right now, is trying to help determine that, how gas planets like Jupiter form, but likely they were the first to form in our own solar system. And it's quite possible that Jupiter is responsible, using its gravity and throwing its weight around, of shaping how the rest of the solar system formed. And so if you don't have a big gas giant like Jupiter in your solar system might actually look a lot different. We're not entirely sure. Right now, if you look at Jupiter closely, I'm pretty sure that this patch here is actually a shadow from one of the transiting moons, because I've been watching it move. So I think that's what that is. But when I looked up online, I couldn't corroborate that, so I might not be entirely correct. But you can actually see the moons right now around Jupiter. I'm going to increase the exposure time. So right now we're exposing at 14.9 milliseconds. So this is actually more of like a slow video, more or less. And if I change the exposure on each of the individual frames, Jupiter will get brighter, but so too will the Galilean moons around Jupiter, so that we're able to see them more clearly. So here are the 4 Galilean moons around Jupiter. This is, I want to say, Callisto and Europa, and over here are Ganymede and Io. I believe I am correct. I looked earlier. There's a great Twitter handle that is called Jupiter Moon POS, position, Jupiter moon position, and it tells you in like basically in characters which each of the moons are as they're orbiting around Jupiter, because they move quickly enough that they can be seen just over a couple hours changing position. And that is what Galileo did when he was watching them. So that's why these moons are called the Galilean moons, and it's one of the pieces of evidence that we had, first of all, that Jupiter is orbiting, and it is turning, on its axis, and that the moons are orbiting Jupiter. So that's one of the first pieces of evidence that our planet was round, and we were probably orbiting around the sun, because Galileo was noting that that Jupiter was central to its own system, because the Jovian system is basically like a mini solar system within our own solar system. It's got a ton of moons. I think we're up to, I think I've lost track now to count, but last I checked, it's somewhere like 79 moons. There's a lot of moons around Jupiter, more than the 4 that we just see here. And Europa, this one here, we were talking about this a little bit last week, but we have missions intending to go to Europa, because Europa, we think, has a subsurface ocean. And in fact, there could be twice as much water on Europa as there is on our own planet. We typically think of Earth as being the water abundant world in our solar system, but there's a lot of these watery moons out there. One around Jupiter, there's one around Saturn called Enceladus. We've actually seen ice geysers spraying off of the moon of Enceladus and helping to contribute to the formation of Saturn's rings, and that's the next object we'll be looking at in just a moment. And so we know that these moons have water, which means that if they have life, there are that many more opportunities to find life out there in the universe, because our solar system alone has over 190 moons. So if moons are places we can find life, and if they're that much more abundant than planets out in our galaxy, we know there's that many more opportunities to find life in our own universe, which is pretty cool. All right, let's turn this down one more time so we get another chance to look at Jupiter before it goes away. Not so overexposed. There we go. The cloud bands of the planet Jupiter. We can't see, I don't think, the red spot right now. I think it's on the other side of the planet. Jupiter rotates very quickly, so it's like usually about, I think, 10 hours Jupiter's day. And so we have you can just stand there and watch Jupiter. If you even have like a decently powerful telescope, you can actually watch it turn just through the course of the evening. And that red spot on Jupiter is the largest storm in our solar system. It is so big it could actually consume our whole planet twice. Imagine that. Now, one of the things I wanted to note, I'm cheating a little bit because I'm going to be pulling data off the Juno mission to show you something. Right now, most of the time from Earth, we're always looking at Jupiter like this. We're looking at it from the side. But for the first time, once we got the Juno probe there, we were able to finally see the poles of the planet, which was really cool. And so if I'm going to pull up one of those pictures now, and this is it. This is actually one of the poles of Jupiter. I believe this is the southern pole. We had no idea that it had this blue coloring, which is pretty amazing. And so this is actually one of the poles of Jupiter. We were able to see it with the Juno probe when it was flying around to take these beautiful colors, this marbling on the planet. And it turns out the poles are very blue in color. We didn't know that. Typically, when we're always looking at Jupiter, we think it more of like that sort of tan, sort of caramel color. But yeah, the poles of Jupiter have these incredible vortices that are all spinning around on the bottom, and this kind of blue, this beautiful deep blue color on the poles of Jupiter. So yeah, we weren't able to see the planet from the top before or the bottom, which is pretty cool. But now that we have this orbiting probe, we're actually able to do that. Okay, since Saturn is up, can't miss an opportunity to see Saturn. No matter how many times I see it through a telescope, it is incredible. So I'm going to switch over here to our software. It's called The Sky. This software spoils us. For those of you who, like Ken, for example, who are part of the Royal Astronomical Society, people memorize the sky with their own telescopes, not necessarily using automation. But for those of us who are kind of born into it later, we got all these fancy computers, and it's like using GPS and not have to memorize where you drive. All right, so here we go. Moving the telescope over to Saturn. You can actually see it moving in the video as well. So if you're watching the video feed from inside the observatory, you can see the telescope moving without us even being there. All right, let's bring up Saturn. And here we go. All right, I'm going to change our zoom. I'm going to punch in a little bit more on Saturn. There we go. Amazing. Here we go. Saturn's a lot farther out than Jupiter, about 1.4 billion kilometers. And people saying my audio is low. Let's see if I can pull my microphone in a little bit more closely. Any better? see if I can turn up my own volume here a wee bit. How is this? Do I sound any better? Yes, it's louder. Okay, great. Wonderful. Okay, so here we are looking at the planet Saturn. And Saturn has rings, a ring system. Of course, that's what it's known for. Pretty sure that the rings around Saturn are actually formed by a moon that was destroyed probably about 200 million years ago. So you can think about that. Like in the past, Saturn didn't actually have rings. You could have looked at Saturn probably for most of its life. It didn't actually have a ring. It's one of those things that we just have the opportunity of being able to see now that we live in this particular time when Saturn's moon was destroyed. And we don't know what probably destroyed Saturn's moon. There's two competing theories. One of them is that the moon was either struck by a comet, so there's a large impact that broke the moon and shattered it into a bunch of pieces. So what these rings that you see around Saturn are actually like millions of mini moons that are all kind of floating around the planet. The other possibility is that the moon approached Saturn too closely. Some moons have unstable orbits. In fact, ours is kind of an unstable orbit. Our moon is spiraling out slowly from the Earth at a rate of about 4 centimeters per year. So give it another billion years or so, our moon will actually just fly off into space. It'll just be gone, floating off into the galaxy. So moons can also approach planets. So one of the planets are on one of the moons of Mars is actually going to crash into Mars. I can't remember exactly which one it was now. It's like anyways. So one of the moons is going to crash into Mars in a few million years. But likely what happened is one of Saturn's moons approached too closely, and when it goes to somewhere called the Roche limit, is where the gravitational stress between the two objects is now so great that it'll tear the moon to pieces. And so it's possible that Saturn actually ripped apart its own moon. And those rings are actually spiraling now inward to Saturn. And in a few 100 million years, the rings will be eaten. They just won't be there anymore. And so they'll be gone again. So something very interesting to think about is that if you're around in a few 100 million years, Saturn won't have rings again. And if there's anyone around then, if depending on whether or not we have recorded history, they might not know Saturn to have ever had rings, which is kind of interesting. Now, Saturn has a moon that is unique to moons in our solar system because it is the only one that has an appreciable atmosphere. And I don't know if we can actually see it right now. Let's see if I can crank this up if we're able to see Titan. I think that might be it right here. Let's see. I'm guessing, but I'm pretty sure that's it because it looks like it's along the same orbital plane as the rings. So I think that's Titan down there. Titan, so Titan's one of the only moons in the solar system that has an atmosphere. And if you ever watched like science fiction back in the day, there was always this like great wonder about what was under the clouds of Titan. Right, so it was kind of like this mystery. And so up until recently, though, we had no idea until we landed a probe on the surface of Titan. It's called the Huygens probe, and we can actually now see the surface of Saturn, which is pretty cool. So there are photos that were taken, and it's the most distant object that we have landed anywhere else in the universe. So, of course, we have stuff that's flying out past Saturn out in the universe, but in terms of anything that's on a celestial body somewhere else, that is the farthest one we have. So over here, which I'm pretty sure is Titan, there is a probe there, and that is the most distant human-made object we have on any other celestial body, which is pretty cool. All right, one more planet to add to our viewing. We skipped this one last time, and I don't know if it's going to be very spectacular, but it's kind of in our mind's eye we get to see it and know that it's there, and that is the most distant planet out at the edge of our solar system, which is Neptune. All right, here we go. Watching the telescope move. Let's see how it turns out. Now, we may not see it right away because sometimes when the telescope moves that quickly, it actually outpaces the dome. So we might need to wait for the dome to finish moving first. I think it's caught up, and we might need to increase our exposure. And maybe zoom back. No Neptune. Neptune might be a wee too low yet. I was hoping it would be high enough by now. So right now, Neptune is at an altitude of 11 degrees, and that has a tendency to sort of be the cutoff point to the dome of the observatory. So the actual dropout shutter, so the bottom end of the dome, might actually be cutting off Neptune, but maybe we could come back to it later if we don't see it here. Yeah, it might be a little bit too low. Neptune usually shows up as a tiny blue dot. We might actually have to do an even longer exposure time. Let's see. Oh, I think that might be it right there. Oh, it's actually behind the cloud, it looks like, because it's starting to get... I know there's a few clouds on the horizon, but I think there it is right there. I'm going to zoom in on it a wee bit more. Hang on. Not exactly overwhelming, but there it is. There's Neptune way off there in the distance, which is pretty amazing when you think about it. Neptune is, we were looking at Jupiter, which was just over half a billion kilometers from Earth. Neptune is 4.3, so that planet is 4.3 billion kilometers away. Not nearly as large as Jupiter either, so definitely harder to see. And it was the first planet that was actually found by mathematical prediction. So we didn't know that Neptune was actually there, except when we were looking at Uranus. Uranus was had some strange kind of like oddities about its orbit. And so based on that, there was Alexis Bouvard was a French astronomer that said, hey, based on some of the things that are going on with Uranus's orbit, it's possible that there's another planet out there. And so they predicted Neptune existed by math, which is amazing. Think about that. Someone cranked out some math based on Uranus's orbit, and Uranus was basically saying, there's another planet behind me out there somewhere, and they found it. It's so far away that its orbit is 164.8 years. So let me think about that for a second. Since its discovery, has it even gone around once? It might not have. I have to do math on that. It's barely, if it has, it's barely gone around once since then. But it also has the strongest wind speeds of any planet in the solar system. The winds on Neptune have been clocked at 2,100 kilometers an hour. Imagine that. It's nuts. The other weird thing about Neptune is it puts out 2.6 times as much energy as it receives from the sun. And we don't know why that is. There is some kind of internal mechanism within Neptune that is generating a lot of heat. And there's some theories as to why that might be. Neptune has a lot of methane, and methane on Earth acts as a greenhouse gas, so it's an insulating gas. So it's possible that Neptune is still radiating off heat from its formation billions and billions of years ago, that other gas giants have already radiated off into space. And so it's kind of still catching up. So that's one of the possibilities. But anyways, the amount of heat that's coming off of Neptune is what contributes to its crazy winds. So it's one of the reasons why the winds on Neptune are so strong. And we call them ice giants. So Neptune and Uranus are actually referred to as ice giants because of the concentrations of water ice, ammonia, and methane that are beneath the atmosphere of Neptune. But it's kind of a misnomer because the ice is not cold. When you get down that deep within Neptune, it's actually quite hot. This is like liquidy, superheated, liquidy, but hot, volatile chemicals that are underneath the surface of Neptune. They're referred to as ices because of their volatility. But yeah, and it's the concentration of methane that also sucks red light out of the sun and gives Neptune its blue appearance. But we'll move on because Neptune is pretty far away and it's just a blue smudge. But there it is. It's amazing to think that we can see an object that far away. Before I do, actually, I'll say one more thing. We are trying to use a similar method now. I wonder if I can boost this a wee bit here. Close. We're using a similar method now to see whether or not there might actually be one more planet out in our solar system, which is pretty amazing. We have started seeing weird things in the orbit of Neptune that suggests that there might be one more planet out there, but it might be like really, really, really far away. We're talking the orbital period of Neptune is about 164 years. We think the orbital period of this planet, whatever it might be, could be on the order of thousands of years. Now, the thing is, it's so far away, this other possible planet, that it probably didn't form in our solar system. It's possible that it actually formed around another star and that it is an adopted planet from another solar system. It's probably about the same mass and size as Neptune or Uranus, and it's out there somewhere. And you might think, well, we can see stuff that's way farther away than that. Why can't we see this planet? And the reason for that is because it's so far away, it reflects so little sunlight that we're not able to see it. Remember, we perceive things based on the energy that they emit or reflect. Planets don't emit their own light necessarily. They do emit some heat, but if you get one that's that far out, it's really hard for us to see. So yeah, it might be one more planet in our solar system, which is pretty exciting. All right, this is another test. I've not tried this object yet, but I'm going to give it a shot. I'm going to start moving to some stars now. And the star I wanted to try out is actually a 6-star system that is based in the Big Dipper. And it's called Mizar and Alcor. And this is a bit of an experiment. Let's see what happens. So here is where we are moving to. Here is Ursa Major. Ursa Major is the Great Bear, and within Ursa Major is the Big Dipper, which is technically an asterism. It's not a constellation, but you know, when even I call it a constellation from time to time. But here are the stars of the Big Dipper, which make up the tail of Ursa Major, and one of the stars that is in it is this one called Mizar. But Mizar is actually a bunch of stars all kind of together. There's 2 of them in particular. One's called Mizar and one's called Alcor. If you have really good seeing conditions in the night sky, you can actually see the binary with your own eyes. That's called a visible binary. But even within that, if you zoom on it with a telescope, you'll get even more stars. Let's see if this works. This shows the telescope's motion, both in the azimuth and altitude, so left and right and up and down. And I know when it's settled out, when it finally gets back to kind of these bouncing indicators, which is just the kind of general motion of the telescope from wobbling around. Okay, so we've settled in on our target. Dome is probably moving. All right, just waiting for the dome to catch up with the telescope. And here we go. All right, let's see if this works. Hooray! All right. Now, this is quite bright. So these are the 2 stars together that you're actually seeing in the sky in the Big Dipper, Mizar and Alcor. So they are a naked eye double. So they, to the naked eye, look like 2 stars. But if I can get the exposure down, we should be able to see that there's actually a lot more stars in here. So Mizar in Arabic actually means a cover. And Alcor means the forgotten one, which is kind of sad because that star is fainter than the other one. So that's why it's given that name. Let's see. Here we go. All right, you can kind of start making out some of the other stars in here. Let's see. Might have to go down even a little bit more. These are shifting on me. I think I might still be in a patch of haze. Let's see. You can notice how much more these objects are twinkling too, since we're looking at stars. And that's because of the effect of the atmosphere. And I don't know if I'm going to be able to resolve, if I turn the gain down a wee bit, the individual stars themselves. Looks like not. But this is a good view of both of these individual ones here. I'll talk about them a little bit, and then I'll move on to 2 other stars. So the interesting thing about these these 2 stars are part of a group of stars that are moving through our galaxy all in the same direction. So they're actually part of something called the Ursa Major moving group. So Ursa Major, all the stars in that constellation were probably all formed together from the same stellar cloud, stellar forming cloud that are moving through our galaxy. And they're probably one of the closer groups of stars that all form together near our own solar system that are all moving in the same direction through space. Probably about 300 million years ago, they finished their formation. And these are the stars that are left over that have now spread out through the galaxy, because we can see that all the stars in Ursa Major are kind of all moving in the same direction. So they're probably all the same with the group family of stars. So these groupings here, there are actually 6 stars here altogether that are all gravitationally bound together. So there's one group of stars here and another group of stars here, and together they all form. Mizar is a quadruple system, so the bigger one here is 4 stars, and Alcor is a binary, and altogether they form a sextuple. So, and they're about 83 light years away. So this is actually a group of 6 stars all orbiting around one another together in space. And we found a number of other stars that are about the same distance away as these ones in some other constellations, which together, I mean, from our sky, they look like they're all part of the same constellation, but they're actually part of this Ursa Major moving group of stars that are all streaming through the galaxy in one direction. Now, through the eyepiece, to your own naked eye, you can actually make out more of these individual stars, but I think to the camera is having a hard time resolving them together. But while we may not be able to see individual stars here, in the next pair that I wanted to do, another binary pair of stars, we can see colors between them, which is great because this is a color camera, so that was another chance to test drive this out. So what I'm going to do is move to another constellation. We're looking right now at the Big Dipper, but now we are going to move to Cygnus, the Swan, which is also sometimes called the Northern Cross. So I'll show you where that is in the sky. And we're going to look at a binary star system there that is called Albireo. If I spell it correctly. There we go. All right. All right, so here's the constellation here of Albireo, the Swan. Albireo is also sometimes referred to as the beak star because it's the one at the very head of the Swan. And as the dome, this is the slit of the dome here that's being represented in the sky software. And since it's moved over, we should be able to see it. There we go. That's what I was hoping would happen. All right, let's expose this a little bit more. All right, so this is cool because this binary system as very clearly shows the 2 color differences between these 2 stars. Now, there's been a debate for a while as to whether or not these stars are actually gravitationally bound to one another or if they're just a visible binary. Visible binary means like they look like a binary star to us, but they may not actually be bound together in gravity, by gravity in space. They might just kind of be, they might look like they're orbiting one another, but we're not entirely sure. So the reason why we're not sure is that the 2 distances to these stars from Earth are not quite exceptionally well known. One of them looks like it might be about 20 or 30 light years farther away than the other one, in which case they're probably not orbiting each other. But we're not entirely sure. There's still a debate about this system. If they are orbiting each other, they have an orbital period of about 100,000 years. So it takes about 100,000 years for one to orbit the other. The other reason why there's a debate as to whether or not these 2 stars are part of a binary pair is because they look like they're moving in opposite directions. So rather than one system orbiting the other, so in this case, the smaller star orbiting the larger star, the less massive star orbiting the more massive star, they seem to be both moving in different directions. But that could be because they're co-orbiting like one another. You know, they might have been traveling through the galaxy and gotten wrapped up in one another's gravity. But they look like they're about 415 light years away. And likely the yellower star might be a large star that has begun to move into a later phase of its life. In which case, like, that's the reason why it has started to change color. As stars age, they go from say a whiter blue or whiter yellow like our sun, and eventually will swell up and become red giants. And we know when that started to happen because the color of the star will begin to change. Color is primarily indication of the star's temperature, and as the stars swell, the energy of the surface area is now spread over a wider area, so they begin to cool down. So when you see redder stars in the sky, they tend to be ones that are toward the end of their life, red giants. There's one that's very clearly visible in the summertime called Antares, that's in the Scorpius. The one in the winter that is most prominent is the left shoulder of Orion, which is called Beetlejuice, very prominently red star. And in fact, there's one more I can show you. I'll show it to you on the screen here, but we'll go back to the Big Dipper. If you're looking for the Big Dipper in the night sky, and there's kind of like a quick way to remember, is that if you follow, this star here is the star that's called Arcturus, and if you follow the handle of the Big Dipper, or follow the arc to Arcturus, that is another red giant star in the sky that you can easily find just by following the end of the handle of the Big Dipper. Follow the arc to Arcturus. All right. Speaking of stars and evolving to stellar death, pick out another favorite of ours here around the observatory because it shows up really well in our camera, and that is the Ring Nebula, which is also known as a planetary nebula, and it is a star that has since died, is shedding out its outer layers. And so I'm going to swing over to that one. Change our settings though. Right now we're not doing live stacking right now. Stacking is when I take pictures of an object for, say, a period of time, 5 seconds, 20 seconds, and then we layer them all together. So you basically make like a picture sandwich. And for bright objects like stars and planets, we don't need to do that. But when we start looking at fainter objects, we need to start doing the stacking. So taking the images and layering them on top of one another. And we can do that with the camera. We can't do that with our eyes. Our eyes are always refreshing the light that's coming into them, so things are crisp. But if you're staring at one object for long enough, you can kind of collect the light from it to make a clearer photo. So that's what we're going to do. So let's move over to the Ring Nebula. So question from Alexander about what is happening with Beetlejuice these days. So that's a good question. So back last October, there was a question about whether or not Beetlejuice might be exploding. So we know that that star is very near the end of its life, and it could explode in the astronomically near future. Now, when we say that, the astronomically near future, that could still be, a million years from now. But that star eventually will explode. When it does, when Betelgeuse finally blows up, it will likely outshine the full moon in the sky for 2 weeks. It would actually be visible in the daytime, even if it exploded, say, during the summer when Orion typically is not out in the daytime, or not out in the evening. So, so we thought maybe that's what was going on or starting to happen, because Betelgeuse had all of a sudden dimmed in brightness a lot. And we had never seen a star dim in brightness so much before. Well, that had never happened. And so we were really interested. We're like, hey, maybe this is happening. Maybe Betelgeuse is finally on its way to exploding, which was, that'd be really cool. But it, unfortunately, that's not what happened. It looks like maybe it burped. So it might have just sprayed a bunch of material out into space. And so that's possibly why it was occluded by dust, because it seems to be brightening again. All right, one of the other things that we're doing with live stacking is we apply some corrections to our individual photo frames. One of them is called a dark, which I'm loading up right now. Oh, wow, that was really bright right away. And one of them is called a flat. The dark removes electronic noise from the camera. And those are pictures that we've taken earlier where it knows that it's basically just mapping out dead pixels and noise that's introduced from the camera. By noise, I don't mean like sound, I mean electronic noise. So like kind of like some of the fuzz that you see here in the image. And so that's why as these images expose longer, you'll see the fuzz will begin to disappear and the colors become brighter, and that's the reason why we stack images. The other one that we use is called a flat, and I've got one loaded up here too. And where the dark will remove electronic imperfections in the camera, the flat removes physical imperfections of the light, so like dust particles that might be trapped inside the camera, and it can map those things and remove them. Over here, for example, if I didn't have the flat applied, there's a couple spots of dew that have formed inside the camera, and it actually helps to get rid of them. So here we go, look at this, amazing. It's one of the things about this nebula, it's so awesome. It's a very forgiving target because it's so bright. And so here we are looking at the Ring Nebula. Some of you might be able to have seen this one a couple of weeks ago. I think we were able to look at this last week. I think we missed out on it because it might have been a bit cloudy. But yeah, so this is a star at the end of its life. It has shed off its outer layers into space. This is not a supernova. So really massive stars, usually on the order of about 5 to 6 times more massive than our sun. What will happen is that as they are burning hydrogen into helium and then progressively heavier and heavier elements, because that's what massive stars do, they will eventually start forming iron. And iron is like poison to a star. It's the tipping point on the periodic table where a star begins to suffocate itself. Iron begins to form in the core, and stars can use energy from the fusion of heavier elements up until iron. Fusing iron doesn't produce any more energy, and so the stars start starving to death. And when enough of the iron forms inside of the core, there's a balance between the outward energy of the star versus gravity that's trying to crush the star in, and that balance is lost. And within a few minutes, the star will literally collapse in on itself. The core will collapse in the middle, and the star will rip itself to pieces in an explosion. Stars like this one here was not heavy enough to do that. Our sun won't produce iron. These stars won't produce iron either. So what happens instead is they just kind of more gently go off into the night. They slowly breathe off their outer layers over the course of a few million years off into space, and then we can image those layers. The different colors represent different kinds of gas. So the outer layer here is probably remnants of hydrogen the star didn't use. The interior layers here are probably more like oxygen, this green color. And you might ask, well, why is there any hydrogen left at all? And that's because more massive stars are actually not super efficient. They're so heavy and so massive and putting out so much energy that a lot of the hydrogen is kept in the outer layers of the star. It can't circulate back into the core and refresh the core with more energy. Stars that are really good at doing that are tinier stars. Red dwarfs in particular, they circulate a lot of hydrogen back into the core. And as a result, red dwarf stars can last for trillions of years. Our star will last for billions, and then heavier stars will last for millions. So each order of size of the star can be like a whole order of magnitude more in terms of their length of life. And so we have found some stars that are probably, some of them are as old as the universe. They were born billions and billions of years ago. And they're still burning, and they'll be burning for a long time more. We wonder if stars like that, red dwarfs, because they last so long, if they might be ideal candidates to find life. Because they're so long-lived, it gives life that much more opportunity for them to evolve, for life to evolve on those planets. But we also have seen that red dwarfs are not particularly good places necessarily for life, maybe because they give off so little energy that planets to be in the habitable zone where it's warm enough for water would have to be so close to the star that they actually become locked. So one side of it always faces the sun or the star, and one side of it doesn't, or they might be very slow. Mercury is almost tidally locked to our own sun. It rotates, but very slowly, and so one side of it is always being cooked by the star, and so they may not be great, which kind of sucks, because red dwarfs are the most common stars through our galaxy. Okay, so these parts on the edge here, I don't know if you can see where there's sort of like a fainter edge, but this is where the layers are being stacked, so the edges here are being missed because the pictures are being rotated, locked all the stars. So, as the telescope is looking at an object, eventually it's going to move slightly because the telescope is not rotating with the sky. Our other camera has a derotator, so as the sky is moving, the camera actually rotates with the sky. This one doesn't. So as we image an object, the sky actually, or the pictures need to be rotated to match the image. So right now we've stacked 15 pictures. Each of the exposures is 20 seconds long, so we've already got a few minutes of time that are already layered together on here. I'll bet you I can bring it up even more clearly. Oh yeah, look at that. Mince down. Stretch the image out a little bit. That is pretty cool. Wow. That is awesome. There you go. Isn't that amazing? A dying star. The Ring Nebula is about 2,500 light years away. So remember, this light left this object that long ago, and now we are looking at it all this time later. Digging into the past, the memory of the universe. That's what light is. Light is ultimately a memory of the universe. Okay. Yeah, Dr. Wu's here. Hello, Dr. Wu. So as Dr. Wu was saying, yeah, because the other telescope, this camera is mounted on the periscope. So it's literally a camera that's looking through the eyepiece. This is where you'd be looking through, and that's why it doesn't rotate like the other camera does. It's not on a device that can be turned like that, like the other camera can. There you go. Okay, Ring Nebula. Amazing. Let's see if we can pop the colors just a little bit more. Actually, might be able to turn them up here a bit. Amazing. Yeah, sky conditions today are definitely better than they were last week. We were fighting with a lot of haze in the sky. This is really clear. So in about 5 billion years from now, our sun will start looking like this too. And if there's, say, some civilization that is within range of us, that has evolved over that period of time, let's say, I don't know, the Orion Nebula. So the Orion Nebula right now is producing stars, and those stars are brand new. It's about 1,500 light years away from us. So they definitely have a view of our solar system. So in 5 billion years from now, that would put their solar system at about the age that ours is, and ours at the age of this one. And maybe they'll be taking a picture of us. Maybe there's someone right now that is about to be evolved or will be evolving in the Orion Nebula, and they're going to be taking a picture of our own star after all this time, knowing that we've taken pictures of them all this time, which is kind of neat. All right, let's move on to another nebula. So this nebula we couldn't see last time, and it is called the Swan Nebula or the Omega Nebula. And it looks awesome in the camera. If it turns out, last week it got clouded out, so I really hope that we're able to see it this time around. And I might change my exposure settings for that one. Yeah. Yeah, what I've done, if I've changed something, I don't know if you can see it on your side, but I changed a setting on the camera. It's called binning. For those of you who are interested in photography, what binning does is it actually groups pixels together. So it lowers your resolution, your overall resolution, but it means that the light from 4 pixels can be gathered together into 1 pixel. So you sacrifice image resolution, but you gain a lot more sensitivity to the light that's coming in. So the more distant the objects or the fainter that they are, then we'll sometimes change to our binning so we can cheat a little bit on our light. It won't be quite as crisp an image, but it means that you might be able to see it more clearly. All right, let's move over there to the Swan Nebula. Find and down. All right. As we're moving around, actually, one thing I'm going to point out. So, Sky, as this software is called, it's literally called the SkyX. We talked about this a little bit last week, so but we weren't able to actually see the nebula. So just want to touch on this again. We're looking into the disk of the galaxy right now. So here's the Milky Way. The Milky Way is a spiraling cloud of stars that holds anywhere between 100 billion to 400 billion stars. And we're inside of it. We're about 1/2 to 3/4 of the way out from the center of the galaxy out toward the edge. And what we're doing is when we look along the edge toward the center of the galaxy is down over here, we're looking through the spiral arms. There are 4 spiral arms to our galaxy. So there's 2 of them on our side that we're basically looking through before we see the center of the galaxy. But that's where all the raw material is that makes new stars. So whether it's the dust and the gas that's pulled together by gravity that then makes new stars, that's where they are going to be. So a lot of the star forming regions that we look at are going to be along this disk of the galaxy, because that's just where the raw material is to make them. And that's what the Swan Nebula is. So Swan Nebula, it's also called Messier 17, or the Omega Nebula, is actually a star forming region. So it's about 5,000 light years away, and there are stars that are being born in that nebula. So let's see what it looks like. Okay, clear. There, that's the old picture. And now we'll start stacking Swan. Have we finished moving the dome yet? It has finished moving. Okay, so this should start showing up. Oh yeah, look at that. It is there. Okay. So let's turn our stretch down a little bit overstretched. Yeah, so good question from Guru Baran. Sorry if I'm pronouncing your name incorrectly. So about green. Yeah, a lot of green does show up in astrophotography. There's a reason for that. So it's actually the way that color sensor chips are built on cameras. So pixels on cameras are built in clusters of 4, and you have RGB within that 4. But there's only 3 colors in RGB, so they throw an extra green pixel in there. Oh, okay, Guru. There you go. Like a wizard or like a master, a guru. So what they do is they actually throw that extra green pixel in. So cameras tend to be already like sensitive to green color, and that is why you get a lot of extra green that does show up in astrophotography, because cameras are just built that way. They're more sensitive to green color. So in a lot of astrophotography, processing software is software to specifically remove and balance the color green. So there you go. All right. So the images are stacking, so that's good. Sometimes what will stop an image from stacking is if it can't see the stars clearly enough. So if we don't have a good enough visible quality, it's like, I don't know how to align these pictures, and so they won't layer them on one another. So as the image is resolving, a little bit about the Swan Nebula. From end to end, it's 15 light years across. Imagine that. So just to fly from one side of the cloud to the other would take you 15 years at the speed of light, which is incredible. It gives you an idea of just how massive these star-forming regions really are. There is an open cluster of stars inside. So that is a cluster of stars that have already formed. And an open cluster means that they are very loosely to maybe not even gravitationally connected to one another. What usually happens in nebulas like this is that when the stars are born, they then float out into the rest of the galaxy. There's not a dense enough pack of them to stay together. They literally leave the nest. They are born and then they fly out of the cloud and away into space. And so that's what happens. So there is a cluster inside of them that's quite large, and that cluster is made of very bright stars that are actually illuminating the gas. So the reason why we can see this would just be dark gas. There's no reason for us to be able to see this unless there was light coming from it, and that light is actually from the stars that are inside of the cluster, of that one particular cluster that's creating the illumination of the cloud. And that there's about 800 solar masses, so about 800 masses worth of our sun that inside that are glowing. And there's probably about 1,000 stars in it that are still forming. So there's another whole bunch of them. And the ones that have formed probably just formed within the last million years. So this is actually a really young group of stars. It takes about 10 million years for a baby star to be born. 9 months for a baby human, but about 10 million years to make a baby star. And so these stars are really new. Like the ones that have just started shining have just kind of come into being. Let's see if I can get this a little bit clearer here. Oh, there we go. And I might bring down the green a wee bit. There we go. Really started seeing it resolve now. Now, if there are planets in a cloud like this, in a star-forming region, they will likely all still be gas giants. So gas giants are the first planets to form, typically in a solar system, like we're talking about Jupiter in our own. So probably not really any terrestrial planets that have finished forming inside of a cloud like this yet. So like nothing probably living there, really. But there could be eventually. So a lot of these in these clouds, we've actually seen pictures of star forming. Of solar systems actually forming within gas clouds like this. bring my mids down a wee bit more here. So our sun would have also formed inside of a gas cloud like this. And that cloud is since gone, because what happens is once all the stars form, they start giving off enough energy to actually clear the cloud out. So it'll be gone. And so it takes it all away. And basically just vaporizes it off into space. But yeah, one of these clouds can form thousands of stars, which is pretty amazing. I'm going to let it expose a wee bit longer. I feel like we can get a little bit more in this area down over here too. Yeah, so the color, yeah, what about why the red coloring? So most of the raw material that makes these stars is hydrogen, right? That is the most efficient gas for stars to fuse together because it is the lightest, so it's the easiest to fuse and gives you the most energy. So that's pretty much the main fuel of stars. When stars stop burning hydrogen, that is when they move off of what's called the main sequence of their life and begin to evolve into red giant stars. Some of these stars that actually, this is the cool thing about these star forming regions, is that some of the stars are so massive, which means, remember, they are short-lived. It's counterintuitive. Even though they have more stuff in them, they are shorter-lived stars. And so some of them are so massive that they're a supernova that will actually start to go off in these regions while other stars are still forming. So you can have some stars that are still being born and some dying all simultaneously within one of these clusters. Supernova, especially if they start going off, will start to spread out the rest of the cloud more quickly. So if you start having more supernovas in a star-forming region like this, it can disrupt future star formation. And the reason why it's red, I'm tangentially going around to your original question, is because hydrogen glows in red when it's excited by stellar energy. So that's why a lot of these nebula kind of look almost like a blue or, like a magenta or red in color. And we can see these star-forming regions like this in other galaxies. So when we look at pictures of like the Andromeda galaxy, you can actually see these pink spots along the spiral arms because they are the star-forming regions that we are seeing from that far away. Stretch it out a wee bit more. I don't want to lose too much of the black here, but that's a little bit too, because I knocked my green down too much and now I'm getting too much blue. So yeah, I'm pushing the stretch a little bit too much here, but you're getting to see a little bit more of the structure of the galaxy that way, or of the nebula. Let it down just a wee bit. I'm going to reset my settings here for 1 second. So yeah, there it is. All right. Okay. Well, there's one other nebula I wanted to show you that we weren't able to see last week as well, and that was the Eagle Nebula. This one is amazing because there's a real prominent star-forming region that's inside of it. And so I wanted to check it out because it's also a pretty bright target to be able to see. So we'll go there next. All right. So again, like we were saying, these star-forming regions are along the disk of the galaxy because that's where all the stuff is, the gas, like that hydrogen that we were talking about. This is where it all is spiraling around the center of the galaxy. That's how we're going to find most of the star-forming regions there. So we don't actually need to move the telescope very far at all to get between these two nebula in the sky. And we'll clear this one and start over. You can see this picture was taken while the telescope was moving, so that's why we got this streak of stars, although it does look pretty cool. All right, so it's one. Let's make sure that we get a stack. So wait for one more frame to come through. And we are stacking. That is a good sign. All right. See what we can see in there. Yeah, so these are the pillars here that I wanted to center in on. So just wait for them to expose a little bit more, and we'll start getting more structure in there. I don't know if I loaded the right flat for this. I don't think I did. That might help a little bit. Okay, starting from scratch. Ignore that first one. Yeah, I think I didn't have them in because even on the first picture, I'm already starting to see more stuff. It is very pretty. Oh yeah, about the Eagle Nebula, actually. I'll show you a picture after. I'm not gonna show it now because it'll totally spoil it. But there's one of the most famous images that the Hubble Space Telescopes took when they first launched it was of the Eagle Nebula, specifically the pillars in the center, which are called the Pillars of Creation, because that's where a lot of star forming, activity is happening. And then, like, I think it was on the 20th anniversary or 25th anniversary of Hubble, they reprocessed the image with newer camera equipment because as Hubble was in space, they were actually doing missions to it with the space shuttle to upgrade some of its gear. And one of the movies you should watch about the last servicing mission to the Hubble Space Telescope is an IMAX film that you can still get in non-IMAX form, and it's called Hubble. And it was 2009, the Space Shuttle Atlantis doing the last servicing mission to the Hubble Space Telescope to install the Ultra Deep Field camera. And it's an amazing movie. You should totally check it out. All right, let's see if we can get some more of the nebula in there. There it is, right in there. You can see the pillars. Let's see if we can get some more. Yeah, so there it is. You can see the three of them here. And so this, as this begins to, or continues to expose here and gets a bit brighter, I'll just talk a little bit about it. So the Eagle Nebula is also Messier 16. Funny story about this. We talked about this a little bit. Yes, that is narrated by Leonardo DiCaprio. That is the one. Is it 2010? Okay, it's 2010. But yeah, it's... anyways, Messier 16. So we talked about Messier last week. Charles Messier is this funny guy because he spent his whole life discovering, or his whole astronomical career discovering things that he wasn't looking for. He was trying to find comets. And so he started like making lists of things that just weren't comets. He's like, okay, that's not a comet and that's not a comet. And as a result, it created like one of the most famous stellar or like categories of deep space objects that we have. And they're great ones because they're ones that like you can see with even like a moderately powerful telescope, which remember when all these people were discovering this stuff like hundreds of years ago, they're using stuff that's even way less powerful than what you could get now with just like a backyard like telescope, right? And so he found all these objects, and sometimes people will do like a Messier challenge to go and find all the objects because they're really easy to pick out. Anyway, so this is one of the ones that he found. It's 70 light years across. So whereas the Eagle Nebula, or rather the Swan Nebula, was 15 light years across, this one's 70. So this is a star forming region that's 70 light years across, which is that's incredible when you think about that. It's just amazing. And so there's probably up to 8,000 stars that are inside of this star forming region. Think about that, 8,000 stars. One of the largest stars that's been observed in the cluster is a star that's 80 times the mass of our sun. So a star like that will put out like hundreds of thousands of times the luminosity that our sun does. I heard a figure once that said if you were on a planet that was orbiting a star like that at the same distance that our Earth is orbiting those stars, the light would be so bright from it that you could be facing your back toward the star with your eyes closed, and the light would be so bright that you could see the bones in your hand. It would shine right through your whole body. That's how bright it would be. Of course, you wouldn't survive, but just to give you an idea of how much energy these stars put out, it's pretty amazing. So yeah, 80 times the mass of our own sun. There was some debate for a time as to whether or not the pillars were still in existence, because there are a number of supernovae that have gone off in the Eagle Nebula, and they were wondering whether or not the pillars have actually been destroyed since. And that light has not reached us yet, the light of the destruction of the pillar. But most recent studies on it figure that they actually are probably still there. Let's see if I can get some more out of it here. I don't want to cut the blacks too much out. So yeah, I can still kind of see it in there. The star-forming pillars in the Eagle Nebula. It's not quite as clear as I hope it would be, but it is there. What if I bring the blacks back and the mids in a bit more? Nope, that's the opposite of what I want to do. If I bring the reds up a bit, we might get more of it in there. Not too much, but a little bit of a contrast. Yeah. So yeah, you can definitely see the outline of the three pillars now. But these are some of the most active parts of the star-forming regions that are out there. Again, 7,000 light years away, the Eagle Nebula. Okay, I will show you that Hubble photo, and then you're going to be like, holy smokes. But remember, the Hubble Space Telescope costs billions of dollars, and it's in space. That's why I can see these things as clearly as it does. So this is our view of Jupiter earlier. Yeah, so this is the updated Pillars of Creation image that was done by the Hubble Space Telescope. So those are the three outlines of the pillars that we're looking here through our own camera to give you a sense of kind of what they look like. But yeah, this picture is astonishing. What an amazing image. Go back to ours. Just to compare and contrast. So yeah, those are the outlines of the three pillars there that are in that picture. Why is it called the Pillars of Creation? Again, because they have sort of like a pillar-like shape to them, so they're kind of standing out from the nebula, and that in those regions is where a lot of the active star formation is happening. Stars are being created in the nebula, and that's kind of where that's going on. Okay, so kind of the opposite then. Last week we talked about star clusters, globular clusters in particular. So where open clusters form within these nebula. So those are new stars that are then forming out into the universe. These are old stars that have clumped together kind of at the end of their lives. And this one we weren't able to see last week because it was cloudy. But today we should be able to see them. So here we go. Let's see. Pick my settings. Yeah. Can probably do 4. Okay. Let's keep it there for now. Okay, so and here we go. All right, moving to a different part of the sky. And why is that? Okay, so remember, star-forming regions kind of fall along the disk or plane of the galaxy. Globular clusters are the opposite. They kind of orbit around the galaxy in like a big clump. There's there's probably about 100, I think there's about 150 known globular clusters that orbit chunks of stars that kind of orbit around the halo of the galaxy. And let's clear this. Let's start from scratch. There it is. Actually, might have still been moving on that one. Let's start over. Reset our settings. All right, here we go. So this is globular cluster known as Messier 15. It is 32,600 light years away from us. So far away. That's typically the case with most of these clusters because they are orbiting around this core of the galaxy. And the core of the galaxy is about that far away from us. We are about 30,000 light years away from the center of the galaxy. All right, let's stretch things out a wee bit. So our images are stacking, so that's a good sign. Bring up the brightness here. Let's turn down our blacks. Now, why am I doing this? So if you, I don't know if you can see can you see the slider bars in the view that I've got? You can. Okay, cool. So the slider I'm bringing in from the black side. This is kind of bringing back the black background because a lot of this part you're seeing here in the histogram, this is what this is called. A lot of this is just sky glow and light pollution and stuff. So basically what we're doing is telling the computer to ignore that part of the exposure so that we can see the stars themselves more clearly. There you go. So clusters like this, there are, say, in a star-forming region like the Eagle Nebula or in the Swan Nebula, you might have hundreds to a few thousand stars that form in one of those regions. And remember, they are not necessarily gravitationally bound to each other, so they will spread out into the galaxy. Clusters of stars like this, though, there could be tens of thousands of them that are inside, kind of like, you know, all stuck together. This nebula, or this globular cluster, has, I saw an estimate, I think about 50,000 solar masses. Let me double check that just to make sure that I'm right. Let's see. Dun-dun-dun. Oh, it's a lot more than that. It's almost 500,000. Yeah, it's huge. Yeah, so like huge mass of these stars, like all clustered together in one place. The reason why I brought this one up is that it is potentially has a black hole in the center. So there's about 500,000 solar masses worth of just stuff inside of this star cluster, but it is probably about 100,000 stars, because remember, some of them are going to be more massive than our sun, some of them less so. And at the center of it is one of the globular clusters where they're pretty sure is likely a black hole in the middle of them. So you can think of it as like a mini galaxy made of really old stars. So clusters like this can have black holes in the center of them. The black hole at the center of our galaxy weighs about 4 million times the mass of the sun, whereas a black hole in the center of one of these is going to be, they call them intermediate size black holes. So not stellar mass. Those are ones that might be like just the mass of a couple stars, like say 30 stars or whatever. But these ones are like say 100,000 times the mass of the sun. And it's possible that they help to give the cluster its shape, black holes like that are in the center. In terms of radius around, we think that the diameter or the radius of this one is about it's about 150 light years across. So from end to end, that's how far apart it is. Well, when you think about that, that means that there are stars that are packed so closely together that in between, say, the same distance that you have between us and our closest neighbor star, which is Proxima Centauri, there's nothing. But within 4 light years radius or distance in a star cluster like this, you might have a few hundred stars or a few thousand stars. It's incredible. The sky inside of a globular cluster like this would be astonishing. There'd be so many stars all over the place. We don't know if planets with life can exist in clusters like this. There might be too much radiation, so it may not be possible. We've done some more stacking, so we can actually probably brighten this up quite a bit more. Oh yeah, look at that. Whoa! That is awesome. There you go. Look at that. Amazing. All right. So very young stars being born in nebula, very old stars clustered together in these globular clusters. And we don't know exactly how they form. We think it's possible they form from galaxies colliding. So we know that our own Milky Way galaxy probably collided with smaller galaxies in the past. That's probably how some galaxies grow. They merge together with other dwarf galaxies or tinier galaxies. And it's possible that those mergers create these kind of clusters of stars that then orbit around the halo. It's sort of like the debris of the merger that's kind of spread out and orbit around the galaxy. Just like when you actually blend food together, you're gonna have chunks that are kind of left over, and it's possible that that is why these clusters of stars form. But again, they're very old, so these are stars that are near the end of their lives. It's also why you probably have a big black hole in the center of a cluster like this. Stars will also merge together, and sometimes those mergers create supernova and more black holes. And then if you have a black hole in the middle like that, it might start accumulating more material, eating more stars, and then of course that's how black holes get bigger and bigger and bigger, is by eating more stuff. In fact, I saw a news article recently. It said, I think we've seen one of the largest black hole mergers ever. It's 2 supermassive black holes at the center of a galaxy all coming together. It's amazing. All right. Okay, do one galaxy, and then I think the moon might be high enough to check that out. So, because I knew it was up earlier, so it might be high enough to actually see now. But we're going to check out M33. This is a galaxy called Triangulum. It's the second closest to our own galaxy. The closest to us is Andromeda, and last week we weren't able to see it. Now, M33 is not a very bright galaxy, so I don't know how well it will turn out. But let's give it a try and see what happens. Space! All right, here we go. All right, going to reset our images because we're probably going to still catch part of the cluster in this one. So we'll just start from scratch. I'm going to clear that one out. Here we go, starting over. So one of the things that I mentioned last week about M33 is that there's kind of a fan theory is that M33 is actually the Star Wars galaxy. The reason for that is that in episode 1, so in Phantom Menace, in one of the scenes of the Galactic Senate, there are the aliens from E.T. are sitting in there. And the poster, which kind of suggests that the ET aliens are actually like part of the Star Wars galaxy. And then if you looked at the original movie poster for ET, it said that it was a story 3 million light years in the making, which is more or less the distance to this galaxy. And because of that theory, new maps of the Star Wars galaxy now look like Triangulum, which is kind of interesting. We have a picture of Triangulum that we took briefly, so if this doesn't work out, we can actually show a photo of it. So let's see. Yeah, this might be really, really faint, but we'll give it a try. So Triangulum's quite a bit smaller than our own galaxy. We think it's about 60,000 light years across, and as opposed to our own, which could be anywhere from 100. I think the most recent estimates I've seen on the Milky Way are closer to about 150,000 light years across. Probably it's possible that Andromeda is actually that the Triangulum is a companion of Andromeda, so the two might be gravitationally bound to one another. And estimates put it somewhere like around 40 billion stars, which when you think about it, it might be only a tenth of the number of stars in our own galaxy. So it is quite a bit tinier than us. Now it is in here somewhere, but this might have been a little bit of an overambitious target. I don't think I'm not sure if it's actually going to turn out or not. So you can kind of make out it's there. What's something unique about M33? It was discovered on August the 26th. I can't remember what year that was, but it happens to be my birthday. So think about that. Somewhere in history, I was born on the day that Triangulum was discovered. I wrote that down. It's a total cosmic coincidence. I'm like, oh yeah, there you go. That's my birthday. Yeah, so this is not showing up super well. This might have been, let's see if I can get a little bit more out of here. Oh yeah, well, it's there. It is in there somewhere. That is the galaxy. I'll bring up a picture. We showed this one last week, but I was hoping that we'd actually be able to see it through this camera, but I don't think it's going to. Here it is. So here's an image of Triangulum. You can see the spiral in the galaxy. So here are the spiral arms here. This is probably a few minutes of exposure on our big astrophotography camera that's attached to the observatory. And those three stars, you can actually see them here in this image. So yeah, I think it's going to be a little bit too faint to show up in this camera over a shorter exposure. You're all going to be sitting here for like an hour before we can see anything super well. So maybe we'll move off of that one then. Okay, so what's next in my list? Let's see. Oh, I skipped a cluster. I skipped a star cluster I was going to show you. Let's go back to that one. So there's one other star cluster I was going to show you. Rather than being a globular cluster, this one is actually two open clusters that are kind of floating around each other. It's called the double cluster, and it's quite bright, so we should be able to see that one pretty clearly. And we weren't able to see that one last week either. It was also clouded out. All right, here we go. So again, reset our picture settings for the next image. Oh, there's some like intense questions going on here, like dark matter and stuff. All right, and there it is. Moving stars. No, just kidding. Clear. Our dome is still moving. So dome has not yet caught up with the telescope. Still waiting for it to go. And there it is. Okay, so now we're on the other side. So we'll clear this out again because this is literally looking at nothing. And there we go. Oh, this is the double-double. That's different. That's not what I wanted to look at. I brought myself to the wrong thing. Fine. All right, moving back to the other side. That's actually a really good point. So Godwin was saying, when we talk about trying to answer questions, like, I'd prefer that scientists just say they don't know the answer. Scientists say they don't know things all the time. It's actually one of the ways that we do more science. So if you ever read like scientific articles in journals and stuff, they will often say, here's what I discovered with my research. Here's the open parts that we still need to know more about. And someone else will have to go and answer those questions because I just don't know the answer. And so I was reading up. One of the big things about that recently was actually in response to whether or not we discovered life on Mars. So if you go back and look at one of the first missions that landed on Mars back in the day, it was the Viking mission. And on Viking, we're not actually sure whether or not there were some tests to find life on Mars way back in the day, and they kind of like were inconclusive. And there's a lot of scientists that were debating as to whether or not that worked or not. Like, did we actually discover life back then? So most scientists are still kind of on the idea that it was inconclusive, that test. But it's one of the reasons why we've designed better tests going forward, because we said we don't know. We don't know the answer. Okay, here we are. The double cluster. Now, these are two clusters of stars that are pretty close to each other. Let's see. Are we seeing all of them in this? We are. All right. Let's see if we can bring them up. So they are kind of in here. They are a bit fainter than other clusters, so this might have to stretch it out a wee bit more. Ta-da. Not coming out as clearly as I hoped they would. Let's see. Well, if I were on target, which I think I am, I should be able to see them kind of in here. I might be too much to the center of the image, so both clusters might actually be outside the field of view. Maybe if I can move a little bit. Let's see. Well, let's see. I might be a little bit off with this one. The double cluster is cool because it's two star clusters that are near each other that are kind of like two groups of stars orbiting together. But I'm not finding it here in this picture. I think our field of view might be too narrow to see both clusters together. I might have had to move off in one direction or the other. This is kind of a neat space background. There you go. All right. I was going to see if we can end off kind of on the moon. Let's see if it is up high enough. I also wanted to see if Mars got high enough before the end of the night. It's possible. Let's see. How high is the moon right now? degrees. We might catch an edge of the moon. Let's see if we can find it. Mars, I think, is going to be too low tonight. I was hoping it'd be up high enough by the time we finish, but it's only at 8 degrees. So if you're outside right now, you could go and see it. You can see Mars. It's near the moon, and you'd be able to see it. So after this, you should definitely go outside, try to find the moon, and look for a red point beside it because that is Mars. But unfortunately, it's still too low for us to be able to see with the telescope because, again, it has to clear about 10 or 11 degrees. The moon, although, is a little bit higher than that. So we might be able to see it. See, it just hit 11 degrees. So let's see if we can see even like the top of the moon. Let's see what happens. Okay. And see. Are we seeing any? This is way too long. Exposure time. It's a moon. Look at that. Hooray. All right, let's bring this up a little bit more. Now, if I have my bearings right, I think we're looking at Tycho crater down at the bottom of the moon over here. Let me just move around a little bit. I'm going to go to manual control and bounce around the moon a wee bit here. Is that Tycho crater? I think it is. Yeah, because up there's Plato. So we were looking at Plato crater last time. I can even get this a wee bit brighter. So you can tell how bright the moon is because the exposure time on the other things that we were laying were 20 seconds each. This one, right now, I'm doing 7 milliseconds. So way less bright because otherwise we would be totally outnamed or overexposed. And so this is Plato crater. To give you an idea just of size on the moon, this crater is about 100 kilometers across. And same with Tycho crater that's down here. It's about the same size, maybe a little bit bigger. Oh, Tycho's actually farther south, maybe. Maybe I'm not looking at the right crater. Oh, there's Tycho. Okay, I'm looking at the wrong. Getting lost on my moon. There are Tycho craters down here. That's that one. So yeah, they're also about 100 kilometers across. Now, sometimes we get this question. We're like, okay, wait a second. Can we see the moon landing locations on the moon through the telescope? And the answer to that is no. And to give you an idea why is because of the sizes of these craters. So if you look at a crater like this, if that's 100 kilometers across, the moon landing site, like an actual object on the surface of the moon, is going to be way too tiny for us to be able to resolve from Earth. Now, that being said, there is a rover or orbiter that's around the moon called the Lunar Reconnaissance Orbiter, and it has taken pictures of the Apollo landing sites, and you can see them. Actually, I'll bring one of them up right now because they're pretty cool. You can actually see like footprints and tire tracks from the rovers, the lunar rovers, the moon buggies, if they will. So here's one of the photos here. You can actually see the two areas. So here's like the astronauts. Look at it. You can actually see footsteps and everything, like the tracks and everything. These pictures have been like enhanced since to up their resolution. There's descent stages, the flag. It's pretty amazing. So we do have photos of these things, but you have to actually go to the moon to get them. So to give you an idea of relative power, like even with our telescope, so the smallest things that we can resolve on the surface of the moon are about 1 kilometer across. So even the tiniest features on the moon's surface are still like the size of Burnaby Mountain. So, you know, you're not going to be seeing, even the Hubble Space Telescope doesn't have enough resolution to be able to image the Apollo landing sites from Earth. You have to actually go there. So again, about 1 kilometer across. Those are the tiniest features that we could resolve on the moon's surface. However, to put that in contrast, recently, about 2 years ago, we started on a project called the Event Horizon Telescope. And that was the telescope that took a picture of the black hole at the center of another galaxy. I believe it was M87. There's also an image that we took of our own black hole at the center of our galaxy. Now, those black holes are enormous. Like the one that's at the center of M87 is millions and millions and millions of solar masses. However, despite being that large, they are still tiny enough at that distance that seeing them is really, really hard. So what we did is we linked together telescopes from across the world to basically make a super telescope. Telescopes' power is really, their ability to resolve something is in their diameter. So the diameter of the telescope that we're looking at right now is 70 centimeters. And the width of the telescope gives you a clearer picture. It allows you to zoom in more on objects in space. Well, that telescope was effectively the diameter of the planet Earth because it linked together telescopes from across the planet. It has so much power that it would be able to take a picture of a tennis ball on the surface of the moon. Imagine that. So our telescope, by comparison, is about 1 kilometer across in features, but that telescope had so much resolution, you could like be standing in Halifax and holding up a quarter and we would be able to read the text on it. That's how powerful that telescope was. Now, again, it's not seeing invisible light. It was mainly seeing in X-rays, but that's how we were able to take that picture of the black hole in another galaxy. Cool. Well, we came all the way out into space, and we come all the way back to our own neighborhood here with the moon. That's going to bring us to the end of today's stream. Thank you so much for hanging out with us. How many people are online with us right now? I think earlier it was like, I think there's 80 people here right now in the middle of the night. Well, not in the middle of the night, but some of them might be in the middle of the night if you're coming in from some other part of the world. And so thank you all so much for doing this. We have so much fun doing this with all of you, and we miss you all. It sucks that we can't do this in person with everybody, but we hope to be able to, hopefully within the near future. But we really appreciate that all of you tune in. We appreciate that you're here, that you're a community of stargazers with us in wonder with the universe. Thanks to everyone who is in the chat moderating today. So thanks to Sarah, Zena, Ken, and of course, Dr. Wu for coming in and helping us out, answer questions. And we will try to keep doing this every Friday. And remember, it's sometimes weather dependent, but we'll always let you know. A couple places to know. First of all, make sure you signed up on our mailing list. So there's an email address you can email. It is on our what is the email now? I can't remember it off the top of my head. Anyways, it's on our Facebook page. You can click on there to sign up, which reminds me, you should also sign up on the Facebook page. So if you like our Facebook page, we also post a lot of information there about what's going on with the observatory and when we have Starry Nights coming up. So please also sign up there, and then that way you know everything that's going on. And if you know of a specific target that you want to see at that during one of our Starry Nights, let us know. Make sure it's one that's up. You can usually check that out on like star apps and stuff like that to know that it's visible at a certain time of night at this time of year, and we'd always be happy to throw it in there because we sometimes will debate ourselves as to what we should show, because there's always so many things we can show in one evening. So thank you all so much. Hopefully we'll see you another Friday soon, and signing off here from the SFU Trottier Observatory. Remember to always keep looking up.